Right, question 5. This is a projectile motion type question where the object, this time is a ball, it's launched at an angle to the ground, given it's 30 degrees and the initial speed is 24 meters per second. The vector therefore is fully specified by those two numbers, and it would look something like this. Relative to the horizontal ground. And of course the actual trajectory or the path would be a parabola shape, something like that. We need to think of it in two halves always when we come across these types of questions. Well, I'll just make some room here, otherwise we won't have space. First question then is to find the horizontal component of that initial velocity. In other words, this component along here, this one. So we just need to work out using trigonometry. And this is the cosine function because it's the adjacent alongside the hypotenuse which we're using. So 24 cosine 30 will give us the answer, and that works out to be 20.78. We'll take a couple of figures because we need to use this number again a bit later. But you could of course round that to 21 meters per second as an answer. Oops. Then question 2, the initial vertical component would be 24 sine of that angle 30 degrees, and plugging that in you get exactly 12 meters per second as your answer there. Number 3, the maximum height reached by the ball. Well, to find that, again it pays to think of this as this vertical distance. The path of course does that, and then the important thing about that point of course is that it takes half of the total flight time to reach that point, and also that the momentary vertical component of velocity will be 0 at that point. So we're going to use that information, that idea, to solve question 3. The best equation to use to find this vertical displacement S would be the v squared equals u squared plus 2as equation, realizing that v will be 0 at that point, so it simplifies down to u squared equals 2as. And so rearranging, making s the subject, you'd get u squared over 2 times a, the acceleration. Plugging in the numbers, u is 12, that's the vertical component. 12 squared, 144 on top, divided by 2 times 9.8, which is 19.6. So we get 7.3 meters to two significant figures. Question 4 is asking us to find the time taken to reach maximum height. Now we know that's of course half of the total flight time. And also, since v is 0, we can simply use the first equation, v equals u plus at, this one, but since u is 0 we can just get rid of that, and it simplifies down nicely to u equals at. Solving for t, we'd have t equals u divided by a. In this case it's the 12 divided by 9.8, and that gives us 1.224. We'll just take a few figures here again, because we're going to need to use that number for question 5 to find the horizontal distance. The total horizontal distance, which I'll put along the bottom here. Now to get that, of course, we need to use the horizontal component of velocity, this one here, the 20.78, and simply multiply it by the time taken for the entire flight, 1.224 times 2, so the actual equation would be simply D equals VT, and the V is the 20.78 times 1.224, not forgetting to multiply that by 2 for the total flight time. Plugging that in and calculating it and rounding to two figures, we get 51 meters. 51 meters as the answer. So this brings us to 5B, the last question of this video. Draw a sketch graph of the path of the ball and mark any important points on your graph. The question 2 is asking us to do the same graph, but with an angle of 40 degrees initially, with the same speed of 24. And then on the same axis again, we're supposed to do another one labelled A, which would show us the effect of air resistance on the original 30-degree angle vector. So with those three things in mind, we need to make enough room to do this. We're going to call this vertical displacement S, and we'll call this horizontal displacement X. Now, oops, that's not really very good. With the original data, we calculated the range to be 51, or the maximum. We'll just label that here, 51 meters. So, trying to do this as symmetrically as possible, something like that would be the first sketch graph, and of course we could label some of these points. That midpoint there would be 25.5 meters, and that maximum height reached would be 7.3. I'll put the 7.3 in. Now, the second time, though, if we did the same calculations with a 40-degree angle, we would find that, in fact, the time of flight is slightly longer. And that is because the ball travels slightly further vertically as it's angled upwards slightly more. So intuitively, it's something hopefully you can sort of visualize. If you calculate it, you'd go 24 sine 40 degrees, and that would give you a larger number. It would give you 12 point, no, just try that again. Actually, 15, yes, 15.429 meters per second. Now, if you put that into the next equation to calculate the vertical height gain, it would turn out to be 12.1 meters high. So, you know, there's that longer vertical height gain. Put that in, I suppose. 12.1 meters high. If we follow through the calculations and calculate the time it takes to reach 12.1, and that is 1.57 seconds, that is, you know, a little bit longer than 1.22. That's only half the flight time. Doubling that, of course, gives you a little bit over 3 seconds, and if you then multiply that by the slightly lower horizontal component of velocity, you would still find a larger range of 57 meters. So there are our points. We need to attempt to find the midpoint, roughly here somewhere. Needs to go up and then down to there. It's not very nice, but rather hard to do on the iPad. If you have a piece of paper, of course, and a pencil, it's the best option for this sort of thing. So that's the line T. For number 3, the original 30 degrees, but now we have to consider air resistance. Basically, you're going to get a very similar initial start, but it's going to drop off pretty quickly and just sort of rapidly decelerate down to the ground. It won't be symmetrical. And that is because you've got air resistance acting and therefore both components are retarded or decelerated by that air resistance. Therefore it won't bend the air as long, won't reach the same height, and it certainly won't make the same range. And we'd label that curve A.